Right, good morning guys. So I'm just going to pick up from where I left off yesterday. So we started looking at the final example at the end of chapter 1. And so it's a second order linear non-homogeneous ODE and subjected to initial conditions y0 equals y prime of 0 equals 0. Okay? And we know that the final solution, yx, is just the superposition y g of x, so it's the general solution, plus y p of x, which is the particular solution. And we saw in the first lecture that the general solution must follow the form a e to the minus x plus b e to the minus 2x, since the characteristic equation lambda squared plus 3 lambda plus 2 equals 0 gives us that lambda must be the eigenvalues must be minus 1 and minus 2. So that's those minus 1 and minus 2 go into the general solution as the exponential coefficients. Okay. So these A's and B's will be satisfied by the initial conditions, and we'll do that now. But the particular solution is what we discussed yesterday. And now what we want is the particular solution in the form of this non-homogeneous part. So we want it to be in the form of x squared. And what do we mean by x squared? So x squared is a second order polynomial. So what we want to do is you write down the most general form of a second order polynomial. And essentially what we're doing is we're including terms, all the terms that can come through the differentiation of this non-homogeneous part. So if we differentiate x squared 0 times, we're going to get ax squared, right? So it just stays as x squared, and a is just to capture the kind of generality of it. If we differentiate this once, we're going to get 2x, and so the most general form of that is going to be just a linear function, bx, and if we differentiate this thing twice, we're going to get some constant. Okay. So this is the most general form, and I suppose now is a good time, as an aside, to say if our non-homogeneous part looks something like, say, sine x, then the particular solution for this would be a sine x, that comes from the 0th derivative of sine x, plus b cos x. Okay? So if we differentiate this twice, we get cos. If we differentiate it 3 times, we get back to sine. So this general form captures the non-homogeneous part and all of its derivatives. What if now it was, say, x sine x? Then the particular solution would be, well, it'll be ax sine x. If we differentiate this once, we're going to get a cos term, so plus b. We could get x cos x term, right, from the product rule. We could then just get sine x by itself after 2 times 2 derivatives, and d cos x term after 3 derivatives or 4 derivatives. Okay, so basically all the derivatives that we can get from x sine x through the product rule can be captured in this general form: a x sine x plus b x cos x plus c sine x plus d cos x. Nothing else can come from the differentiation, no other form of function. Okay, and the point relating it back to the beginning of the chapter is that these terms here, or these functions here, are all independent functions. So I can't multiply sine x by a constant to get cos x or x cos x or x sine x. Okay. So the particular solution is of this form. The first derivative of this particular solution, what I'm going to do is I'm going to differentiate this once and differentiate this twice, plug it back into the original equation, and find out match coefficients for a, b, and c. Okay. So the particular solution, ax squared, so the first derivative is going to be 2ax plus b, and the second derivative of the particular solution is going to be 2a. Right? So I plug these things back into the original equation, and I get 2a plus, so 2a times, that's just y double prime, 3 times y prime is going to give me 6ax plus 3b, and the last one is going to be 2 times this is going to be 2ax squared plus 2bx plus 2c must equal x squared. Okay. right? Now I'm just going to match coefficients, so the coefficient here, so I know that 2a is equal to 1, which tells me that a is equal to a half. I know that for the x's, I'm going to have 6ax, that term there, and that term there, plus 2b must be equal to 0. I've used that term as well. And then the last term is going to be 2a, 3b, and 2c. So 2a plus 3b plus 2c must also equal to 0. With a equal to a half, this means that b is equal to minus 3 over 2. And then plugging a and b into here, calculating c is equal to 7 over 4. Okay, so that's about as far as we got yesterday. So the particular solution is going to be ypx is plugging these things into plugging a, b, and c into a particular solution is going to give us a half x squared plus minus 3 over 2x plus 7 over 4. And so our final solution, or our full solution, including the general solution, is going to be a e to the minus x plus b e to the minus 2x plus this thing here, so half x squared minus 3 over 2x plus 7 over 4. Right, now what we want to do is calculate these values for a and b. So we want to calculate the values for a and b. And how do we do that? Well, let's look at the initial conditions. So we know that when x is 0, y of 0 is equal to 0. So what does this mean? So we plug 0 in to the x's, and we get a e to the 0 is 1, plus b e to the 0 is 1, plus a half is times 0 is 0, minus 3 over 2 times 0 is 0, plus 7 over 4. We know this is 0, so we've got one equation, two unknowns. The second is the derivative of this equal to 0 tells us that. So I need to differentiate this thing once. I'm going to get minus a e to the minus x. So just differentiating it, I'll plug in x equal to 0 now. Minus 2b e to the minus 2x plus, so the derivative of half x squared is just going to be x. Yep. Minus 3 over 2. And the derivative of a constant is 0. So I plug x equal to 0 in here, and I get minus a e to the 0 is 1, minus 2b e to the 0 is 1, plus 0 minus 3 over 2 must be equal to 0. So I have two equations, two unknowns. I can solve them simultaneously, and I find that a is in fact is minus 2, and b is a quarter. And you can go back and double check that. We can plug these a's and b's into the this final form here and get a final solution. Okay, so y of x, final solution should be y of x is equal to minus 2e to the minus x plus a quarter e to the minus 2x plus a half x squared minus 3 over 2x plus 7 over 4. Okay, so this is the final solution. There are no constants of integration, or no unknown constants. We've solved for them using the initial conditions. Those are here. And if you like, you can differentiate this once and twice, plug it back into the original equation up here, and see that this actually does satisfy the equation if you're feeling ambitious. Okay, so there it is. I'll upload another video now covering chapter 2. Thank you. Oh, if you have any questions, send me an email or a direct message on Twitter, preferably. I'll be available kind of as much as possible over the next few days. Okay, bye.